We're going to continue on chapter 5 now, so we're still talking about probability distributions. In 5.2, we're going to get into binomial probability distributions. Okay, now, so some key concepts in 5.2 when talking about binomial distributions. The focus is on binomial probability distributions, as the name of the section implies, and methods for finding probabilities. For binomial probability distributions, finding the mean, the standard deviation, and the variance is actually a little bit more straightforward than what we've seen previously, so we're going to cover how to calculate those. As we've done previously, in this section again, we're going to look at the importance of interpreting probability values and how to determine whether they're significantly high or significantly low. Before we talk more about binomial probability distributions, we first need to cover what is a binomial probability distribution and what four requirements must be met to then determine that it is a binomial probability distribution. So number one, the procedure has a fixed number of trials. You can think of a trial as a single observation. Number two, the trials must be independent of one another, which would mean that the outcome of any individual trial does not affect the probabilities in the other trials. Number three, each trial must have all outcomes classified in exactly two categories, commonly known as a success and a failure. This is not saying that success is good and failure is bad. It's more so that successes fit the outcome that we're looking for. So like toss a coin 2 times and then get heads both times, that's 2 successes, right? And then getting tails would be 2 failures, but it's not necessarily this is good and this is bad. The fourth requirement here is that the probability of a success remains the same in every trial. So this kind of builds on number 2 and number 3. So the probability of a success remains the same in each trial. Each trial is independent of one another. Or in other words, the probability that happened in this one trial does not affect the probability of another trial. So with binomial probability distributions, we need to talk through the notation. So we're going to talk about capital S and F as being a success and a failure. Remember what we just talked about on the last slide. So there can only be 2 possible categories of outcomes, either a success or a fail. The next notation here, the probability of capital S, or the probability of a success, is also equal now to lowercase p. So lowercase p is the probability of a success. It makes it easier that we don't have to write this out every time, but it can be confusing now because we're introducing a new way of writing the probability of a success, but that's lowercase p now. Then alternatively, instead of writing out the probability of a fail each time, we write out lowercase q, because lowercase p and lowercase q need to equal to 1 because they're complements of each other. Every outcome here has to either be a success or a fail. So remember, our successes are represented by lowercase p, the probability of successes. The probability of failures is denoted by lowercase q. So p plus q has to equal to 1, where p is the probability of a success and q is the probability of a failure. So instead of writing out capital P of S and capital P of F, we're now going to start writing lowercase p and lowercase q. Next, N is something similar here. It's the number of fixed trials. And we'll practice identifying what is P, what's Q, what's N throughout this whole section. The next notation here, we have lowercase x again. It's a specific number of successes. We've seen this before in N number of trials. So the restrictions on x then, it can be any whole number, it has to be a numerical value, between 0 and n, where it's between 0 and n number of trials. That x value can be 0, it can also be n, it can also be any whole number in between. So that's also important, it has to be a whole number between 0 and n. So more on lowercase p, more specifically, it's the probability of success in just one of the trials of n. So we have all of these n trials. Lowercase p is the probability of a success in just one of those trials. Similarly then, we have all of our n number of trials. Lowercase q is the probability of failure in just one of those trials. And remember, for binomial distributions, the probability of the outcome of one trial does not impact the probability of the outcome of another trial. Okay, just a little bit more notation here. So the probability then of x, where x is a specific number of successes in n number of trials. So it's the total number of successes in n number of trials. Then we have the probability of x is the probability of getting exactly x number of successes among the n number of trials. Okay, so lowercase p is about success of one trial. Lowercase q is the probability of failure of just one trial. Then the probability of x is the probability of getting exactly x number of successes amongst all the trials. We're looking at all the trials together and then how many successes we're getting, not just on an individual trial by trial basis. Remember again that requirement, each outcome has to either be a success or a failure. We can't have any other option. So these S and F denote the two possible categories of all the outcomes. Okay, so that's all our notation for binomial probability distributions. It's a lot, but we're going to practice using it. Some additional notes here on the notation. The word success is used arbitrarily, right, as I mentioned. So it doesn't necessarily mean that something good or something bad. So based on the wording in the question, we can actually use this idea of a success in either category. It really comes back to the wording of the question, and we'll go through some examples today. So as long as we're clear on what a success is, it could also be not getting heads. That could also be our success. Depending on how we set up the problem, getting success can also be getting the number of heads that we're looking for. So as long as we're clear on denoting notation as S for successes, then success is correlated with lowercase p. Then depending on what we actually calculate the probability for, we'll get a value for p, which is the probability of successes. Then we can just use the opposite case to be represented by q. And we can always find the complement by doing 1 minus p is equal to q. So really denoting either category as success and lowercase p or a fail and lowercase q, as long as we're consistent, we'll still get the right value for the probability of this case and this case. You can almost think of it like not success and fail, but category number 1 and category number 2, where category number 1 is denoted by uppercase S, and then the probability of a uppercase S is P. The other category happens to be denoted by uppercase F, and then lowercase q for the probability of that category. So again, it really is arbitrary. We just need to identify what our two categories are and then be consistent in the notation. Another way we need to be consistent is when using binomial probability distributions, we always need to be sure that x and p are consistent in a way that they both, x and p, refer to the same category being called a success. Okay, so our consistency needs to be that s and lowercase p match up, f and lowercase q match up, but then also p has to be matched up with x. Because when we go back here to this notation on the last slide, the probability of x is the probability of getting exactly x number of successes. So whatever we're calling a success here needs to be aligned with x. It also needs to be aligned with p. Okay, so that's what's meant by this third bullet point here. Before we get into an example of using binomial probability distributions and solving problems in this way, I want to touch on one potential misconception. So binomial probability distributions, what we're looking at in 5.2, this is not the same as a bimodal distribution. If you remember talking about that, I think that was in chapter 3. So bimodal distributions are when we have two data values that occur with the same greatest frequency, where each is a mode, right? Where a mode is the category or the value that appears the most in our data set. When we have two modes, we have a bimodal distribution. A histogram of a bimodal distribution would look something like this, where this is one mode and this is the other mode. So these are the numbers that appear the most in our data set. However, here in 5.1, we are not talking about bimodal distributions. we're talking about binomial probability distributions, where the bi here, so 2, that is because we're dealing with 2 categories only, success or failure. So I wanted to clear that up as maybe a potential misconception. Let's go right into an example and start using this notation, get more familiar with it. We're going to say an adult is randomly selected with replacement. There's a 0.85 probability that this person knows what Twitter is. I do not know what year this is from, but 0.85 probability, it might be even higher today, but let's go with this example. Suppose that we want to find the probability that exactly 3 of 5 randomly selected adults know what Twitter is. Using this example, we're going to answer, does this procedure result in a binomial distribution? If this procedure does result in a binomial distribution, we're going to identify these variables. We're going to start practicing figuring out what's n, x, p, and q. So let's answer A first, and then we'll see if we can answer B. So A, does this procedure result in a binomial distribution? In other words, can we take that information in the question and separate it into only 2 categories? That's the basis, but beyond that, we need to make sure that this question here does fit all the 4 requirements that we talked about initially. So the first requirement is satisfied because the number of trials is fixed. It's only 5. Our next requirement, these 5 trials are independent because the probability of any adult knowing what Twitter is not going to be affected by results from other selected adults, especially when we're selecting adults in a completely random sample that don't know each other, where this person doesn't impact what this person is thinking or if they know what Twitter is. The third requirement, also really important, is that each of these 5 trials has 2 categories of outcomes. Either the person knows what Twitter is, or that person does not know what Twitter is. We can break this into 2 categories. The fourth requirement, for each randomly selected adult, so 1 adult at a time, there's a 0.85 probability that that person knows what Twitter is. For the second person we select, that probability remains the same. It doesn't go up, it doesn't go down. So for each of the 5 people, we'll have a 0.85 probability that they know what Twitter is. That probability is the same for each of our people. So all of these 4 requirements lead us into saying that yes, this does satisfy the requirements for a binomial distribution. Now we can go on to B because we know A to be true. So think about what n, x, p, and q might be. So using the notation we just learned about, n is the number of fixed trials. So we have 5 different people we're going to select. That's how many trials we have. We're going to ask the first person, the second person, third, fourth, and fifth if they know what Twitter is. Those are our 5 fixed trials. So I previously mentioned this variable of x. It will be interchangeably used with the variable of lowercase s, which represents the number of successes. So x and s are used interchangeably. Keep that in mind as we move forward. Back to our notation, x is the number of successes among n number of trials. Because we want to know the probability of exactly 3 people out of the 5 people we selected, do they know what Twitter is, then we're going to count the number of successes as 3. So number of successes, we have 5 people in this trial. If 3 of them know what Twitter is, that's 1 success, 2 success, and then another 3rd success. So far, n is equal to 5, x or s, we use those interchangeably, is equal to 3. Now, importantly, to stay consistent, we're calling s, the number of successes, as people knowing what Twitter is. So people knowing what Twitter is a success. Then the complement to that would be the failure and somebody not knowing what Twitter is. So remembering that number of successes is linked with lowercase p, then lowercase p here is 0.85, where p indicates that a person does know what Twitter is. P needs to be consistent with x and s, and they all are. X and S reflect that people know what Twitter is. Then P is also the probability that somebody knows what Twitter is. So those are all consistent. Then for Q, this is the complement. It's good to put this in wording. So the probability of a failure, what does the failure really mean? That's not getting someone who knows what Twitter is in this case. So the failure is associated with lowercase q. Lowercase q then is the complement of lowercase p. So lowercase q is 1 minus the value of p. So lowercase q, the probability of a failure is 0.15. Okay, so on your own, when you're going to do this, you want to think about the number of trials. You want to first figure out what are we calling successes. Then we need to know the probability of those successes and the probability of then what you're calling a failure. There's some checks we should do now that we denoted what n is, x is, p is, and what q is. So it's really important to be sure that x or s and p refer to the same concept of success. We have to be consistent there. So in this example, we use x or s to count the number of people who know what Twitter is. Therefore, lowercase p has to reflect the probability that the selected person knows what Twitter is. That has to be lowercase p. Then we can check this. X/s, we're using those interchangeably, and p do use the same concept of success, that a person randomly selected does know what Twitter is. It's so important that x and s and p are all reflecting the same concept of success. Now, mentioned previously in the requirements for a binomial probability distribution, we wanted to say that each of the trials is completely independent of one another. Now, if we run into trials where the outcome of this trial does impact this trial, we can still maybe use this binomial probability distribution concept, but it has to satisfy these guidelines. So we have touched on this before as well. So here's our 5% guideline for cumbersome calculations. So when we're sampling without replacement, so we take one person out of the mix, we don't put them back in before surveying the next person. If we're sampling without replacement and the sample size is no more than 5% of the size of the population, we can actually treat those selections as independent and we are using with replacement. Even though in actuality they are dependent on one another, that becomes more cumbersome to have to calculate. If you recall with calculations without replacement, we had to change that value in the denominator. So we had 1 out of 1,000 people, for example. The next case would have to be 1 out of 999. It gets pretty cumbersome to have to change that denominator each time, especially when we're dealing with a ton of trials. So this concept of going from 1 over 1,000 to 1 over 999 is the same thing as taking into account n minus 1 for each trial. I did touch on this initially for 4.2, so if you want to go back for a refresher, I recommend doing so. Coming back here for this application of binomial probability distributions, because the requirement of that is our trials are independent, if we have a sample like this, where the sample size is no more than 5% of the size of the population, and we originally read that it's without replacement, those trials are dependent on one another, we might think, oh, I can't use a binomial probability distribution here. Well, actually, we can. We can treat them independently if this guideline is satisfied. Okay, now to actually solve for the probabilities when we have a binomial distribution, we're going to use one of 3 different ways. The first is we're going to use a formula. Here's our formula. P of x is equal to n factorial over x minus n factorial in parentheses multiplied by x factorial. Once we do this part here in this fraction, we're going to multiply this times p raised to the power of x multiplied by q raised to the power of n minus x. It may look more complicated, but we know how to solve for each of these variables. We know how to figure those out. So n is our number of trials. X or s, same thing, is the number of successes among n number of trials. Lowercase p is the probability of successes in any one single trial. And q is the probability of failure in any one single trial. Now we know how we can find n. We need to make sure that our x or our s value fits these restrictions here. So x has to equal 0, 1, 2, 3, has to be a whole number. It can be 0. It can also go up to n number of trials. If x and n are ever equal, we're basically asking out of all of these trials, if we're getting all of these trials to be successes. If x were 0, that means we have a certain number of trials, but we want to find out the probability of getting no successes out of all those trials. And an important reminder here, lowercase p and q are the probability of success and failure, respectively, for only one single trial. If we had 1,000 trials, for example, you would probably not want to calculate manually using the multiplication rule and saying the probability of first trial multiplied by the probability of the second trial, third, fourth, fifth, all the way through 1,000. So once we assign these variables, we can plug the variables into this equation and then get our probability for a binomial distribution. We can only use this formula if A, we're told we're dealing with binomial distribution data, or B, we looked through those 4 requirements and we checked off that yes, this is definitely a binomial probability distribution. Let's take the same Twitter example now and practice using that formula. We're going to do so in the case that we selected 5 adults randomly, and we want to determine the probability of exactly 3 of them knowing what Twitter is. So remember, we have n number of trials, that's our n value. We're looking at 3 number of successes, or s number of successes, where 3 reflects selecting 5 people for our trials and 3 of them knowing what Twitter is. Then x/s and p need to refer to the same concept of success, and here they do. So lowercase p, or the probability that somebody does know what Twitter is in one trial, is equal to 0.85. The complement to that then would be q, or the probability of failure for one single trial, is 0.15. I recommend you pausing this here, plugging in your values to the formula, and solving for that probability before pressing play. Okay, so now here's our formula that we were given. So p of x is equal to this. Let's start plugging in for n, x, p, and q. So here in this first part of our solution, the probability of 3 number of successes is equal to n factorial, or 5 factorial, divided by n minus x, or 5 minus 3, in parentheses, and then factorial, multiplied by x factorial, or 3 factorial. We're going to multiply that by p raised to the power of x, where p is 0.85, x is 3. Then that is going to be multiplied by q raised to the power of n minus x. So q is 0.15. N minus x is 5 minus 3. Really importantly, do not forget to do order of operations. So do what's in parentheses first, then factorial. So you see in our next step here, 5 factorial divided by 2 factorial times 3 factorial, multiplied by this number and this number, where this is a result of 0.85 raised to the power of 3, and this is the number of 0.15 raised to the power of 2. So we solve for this fraction here, we multiply these values through. Then in our final answer, we're going to round off to 3 significant digits. So our final answer is 0.138. So we have the probability of 3 number of successes is equal to 0.138. Let's also put this into words here, just to clarify. So the probability of getting exactly 3 adults who know what Twitter is among 5 randomly selected adults is 0.138. So to get to this point, we need to confirm that that case was a binomial probability distribution based on those 4 requirements. Next, we figured out our variables. So n, x/s, it's the same thing, lowercase p and lowercase q. Then we use method 1 for solving for the actual probability value, and we use this formula to do so. In using this formula, we were really careful about what's in parentheses, what each variable really means, and then getting our final answer here. So using this formula is certainly an option. I'm going to talk through two more methods here. The second method is using Excel, which is my favorite way. So to use Excel, I made some very detailed step-by-step directions. They're in your student outline. So Excel can find binomial probabilities for you if you plug in the numbers the correct way and use the right formula. So we know all of our notations. We know N, X/S, P, and Q. You can open up functions in Excel and type in these numbers here to a box that opens like this, a window that opens like this. You can do it this way, or you can start typing in the formula directly into a single cell in Excel, where a single cell would be A1, for example. This is cell A1. This cell here, this is cell B3. So it's column B and it's row 3. When you're in Excel and you start typing in one cell, equal sign to set up a formula, then you start typing in BINOM, this will start to populate. Once this populates the correct formula you want to use, you're going to click on it and then figure out what numbers to plug in here. I tried to walk through the steps as best I could in your student outline, so be sure to read that and practice on your own. When setting up these four numbers here, this is X or S, our number of successes, comma, this number here, which is our N value, comma, this number here, which is our lowercase p value, comma, this 0 here, where this 0 is the cumulative value. For the cumulative values we'll use in this class, it'll be usually either 0 or 1. And I'll talk to you about these cumulative values more on the next slide, but these are the four numbers that go into this function, and then you'll get an answer from Excel. It is crucial, though, that you're putting in the right numbers for the right places, or you'll get a completely different answer. Okay, so practice Excel on your own. Go through all those steps and let me know if you have any questions at all. Now, I mentioned I would talk more about this cumulative value. So in part C on your student outline, we go into adjusting the cumulative value to be from 0 to 1. Now remember that cumulative value goes right here in our formula when we start to type this in. The reason we want to use 0 initially is because we're asked about the probability of getting exactly 3 adults knowing what Twitter is. For exactly 3 number of successes, or exactly any number of successes, our cumulative value is 0. When we change the cumulative value to 1, let's see what that really means. When we change cumulative value to 1, we're actually going to calculate the probabilities up to that number of X or S. So for this example, for our case, X is equal to 3, so exactly 3 adults know what Twitter is amongst the 5 number of trials. If we change that cumulative value to 1, what we would actually calculate is the probability that 1 adult out of the 5, or 2 adults out of the 5, or 3 adults out of the 5 have heard of Twitter. So essentially, we're being cumulative here. We're taking the probability of 1 or 2 or 3 adults know what Twitter is. So to kind of sum this up in wording, exactly X or S number of successes, cumulative value of 0. If we're asked up to that number of successes, cumulative value of 1. Let's try this next example. So we previously noted that between the years of 1974 and 2011, there were 460 NFL football games decided in overtime. Out of that number, 252 of them were won by the team that won the overtime coin toss. When a team wins the coin toss in overtime, they're deciding who possesses the ball first. So now we're going to ask, is the result of 252 wins out of these 460 games equivalent to a random chance? Or do we have some significance here? Is 252 wins considered significantly high out of this total number of games? To solve this one, we're going to set it up with a little bit different of a mindset. So we're going to answer this question by finding the probability of 252 wins or more in 460 games. This comes with the assumption that wins and losses are equally likely. Now, in the question, we're not given the probability of the likelihood of winning one game or losing one game. This next point here is something we'd have to assume or be told in the problem. So we're going to assume that a win and a loss, our two categories, are equally likely to happen. We're going to assume that because we weren't given probabilities. We weren't given, for instance, like in the Twitter example, that the probability is 0.85 that an individual knows what Twitter is. We have to have some probability to go off of, so here we're going to assume that wins and losses are equally likely. So in our steps for solving this, we want to go back and make sure that all four requirements do fit for this example to consider it a binomial probability distribution question. If we went through those four requirements, we would see that this is an example of that. I recommend going back and doing that on your own and proving that we can use binomial distribution theories for this example. So knowing that we can, though, the next step would be to figure out all of our notation. So if we have n number of trials, that's 460 games. Because we weren't given a probability in the question, as just mentioned, the probability of winning and losing is equally likely. When two cases are equally likely, it's a 50-50 chance. Therefore, P and Q both need to be 0.5. They both need to add up to 1. Now, in the question, we're asked if 252 wins in the 460 games is equivalent to random chance, or is that a significantly high number of successes? Well, in this wording, if we're figuring out if 252 number of successes is significantly high, remember that definition of figuring out if something is significantly high or low? It's that we look at 252 number of successes or more. I went back to this slide to show you this in wording here. So when determining if we have significantly high number of successes, we're really asking the probability of X number of successes or more if that's less than or equal to 0.05. Now let's go back to our example and figure out if that's less than or equal to 0.05. Now let's go back to our example and plug in what we know for X, so the number of games or more. Okay, so we're back to this slide. We want to find the sum of all the probabilities for each value of X from 252 or more, where the maximum value is the number of trials, or 460. So what this bullet point is really saying is that we have X number of successes, or 252. We have another scenario where we want to figure out 253 number of successes. We have another scenario where we'd want to figure out 254 number of successes. And we want to be finding the probability of all of those, where the wording there is the probability of 252 wins, or 253 wins, or 254 wins. So that or means we have the addition rule, so we'd end up summing up all of those probabilities where X is equal to 252, all the way up through X is equal to 460, all of those whole numbers in between. Because that's the information we're looking for here in this question, the formula method is really not practical, because we don't want to plug in 252 for X, and then 253 for X, and then 254, etc. So because we don't want to do that, really our best bet is to use Excel. That's method number 2. We'll do an example of method number 3, where we use this table A1 in your textbook. We can't even use the textbook table here because n is equal to 460 doesn't fit in the scope of that table. So now we get to use Excel here. That's really the best method for this problem that we're looking at. So for our solution using Excel, and for any solution using binomial probability distributions, we want to figure out our notation. Well, here from the last slide, we know n is equal to 40, the number of games. The probability of a success in one trial is 0.5. the probability of a failure in one of those 460 trials is also 0.5. That's from this wording here that these two cases are equally likely. So when using Excel to solve this type of problem, we need our X or S value, our N value, our P value, and then what do we put in for cumulative, 0 or 1? So out of those, we still need to figure out what do we use for X or S, and what do we do for the cumulative value? Now you might think, wouldn't we use 252 for our X value, our S value, and then use a cumulative value of 1, so we'd figure out the probability of getting 1 win or 2 wins or 3 wins all the way up to 252 wins. So if we did that, we plug in 252 for X and 1 for our cumulative value. Excel would then take all the probabilities and add those together up to the number we put in for X, or 252. Is this really what the question is asking? Do we want to know the probability of getting 1 win or 2 or 3 all the way up to 252? Well, no, we're interested in, is 252 significantly high? So remember, using significantly high, we want to figure out the probability of X or more, the 252 or more wins. How do we deal with this in Excel then? Well, based on what I just explained, there isn't a way to do that in Excel. Because when we use 1 for our cumulative value, it's going to take 0, 1, 2, 3, 4, all the way up to X number of successes. I didn't mention 0 here in this previous explanation, but that's also in that probability. So 0 wins or 1 win or 2 wins all the way up to 252. So we need to reconsider what we put into Excel. So we actually want to use the complement here. Then we know that our successes and our failures have to add up to 1, so we can subtract the probability from 1 to then get our answer. The trickiest part here, what is the complement that we can actually plug into Excel? Well, our successes is that we have 252 or 253 or 254 wins up through 460 wins. That means that our complement then is that we have 0 wins, 1 win, 2 win, 3 win, 4 win, all the way up through not 252 wins, but up through 251 wins. So here's our complement. We get 251 wins or less. Going back to our question, is 252 significantly high? That's really saying 252 wins or more. So our complement to that is 251 wins or less. Take a moment, pause this, and really think through, does this make sense? If you need any help thinking through how we got this, please let me know. So in Excel then, we can enter the probability of 251 or fewer, so that'd be 0 or 1 or 2, all the way up through 251 wins. Our N value doesn't change. We still have 460 games we're looking at total. Our cumulative value, because we want 0 or 1 or 2, etc., then our cumulative value needs to be 1. If we by mistake here use a cumulative value of 0, we'd really be finding out the probability of 251 wins only. But we also want to take into account 250 wins and 249 wins, etc. Now let's plug this into Excel. In any cell you'd like, if you type in equal sign, then start typing BINOM period DIST, this will start to populate. Then it's super important, what am I putting in for each of these 4 values? So the way I did this is I set up all my values here, and then when I type in this formula, I click to what cell I want each number here to refer to. So in this formula in Excel, the first value here needs to be the number of successes. In our case, the number of successes is 251 or less, right? The next number here, separated by a comma, is N number of trials, that's 460. You can also just type in 460 here into your formula, but I typed it up here. And now this formula will refer to whatever is in B1 to do the probability calculation. Separated by another comma, then we need our p-values, the probability of successes. In this case, the probability of winning and losing were equals, that's 0.5. This next really important part of this formula is our cumulative value. We want to know the probability of 0 through 251 wins. Therefore, we put this cumulative value of 1 and not 0. So on this slide, I was setting up this formula. Here, I clicked enter and it calculated this for me. We'd want to round this to 3 digits past the decimal place. So then we get, when we enter 251 or fewer wins out of 460 overtime games, with a cumulative value of 1, the probability is 0.978. We're not quite done. We haven't quite answered this question because here we have 251 or fewer wins, but we're really interested in 252 wins or more. So remember, we need to use the complement rule and take 1 minus this value to get the true probability value that we're interested in the question. Okay, so here's the same information you've seen before. This is the complement to what we're actually interested in. Now we take 1 minus 0.978, that's 0.022. This 0.22 is the probability of 252 or more wins in this number of overtime games. This value is 0.022. That's low. That's less than 0.05, and that's the cutoff we're going to use to determine if this number is significantly high or not. Because this probability is less than 0.05, then it does have significance. In other words, this shows that it's unlikely we would get 252 or more wins just simply by chance. Because this probability is less than 0.05, then we have true statistical significance. The counter to random chance is that we have true statistical significance. If we take this to mean that there is true statistical significance, because it's less than or equal to 0.05, then we'll go to this next bullet point here. I do want to remind you that the 0.05 is somewhat arbitrary. We could have used 0.01. We could have used 0.005. The questions that you'll work on will need to tell you what probability value exactly is considered significant. By default, it is usually 0.05. So then if we effectively rule out that this does not happen by chance, then we're left with a more reasonable explanation that the team winning the overtime coin toss does actually have a better chance of winning the game. Now, as you're getting more acclimated with Excel, on your own, I want you to practice with average, median, mode, and variance, and try to find some other formulas we've been using this semester. Okay, so we use the formula method, we use Excel. The formula method isn't always practical. Excel is always practical. We also have this third method of using the table in your Appendix A. It's table A1. In table A1, there's a list of all the binomial probabilities for a select value of n, and then also a select value of p-values. In our football example, we had n is equal to 460. We definitely couldn't use this table for that example. But if n is 8 or less, then we can use that table. Not only do we have to have an n value that's 8 or less, we also have to be working with specific p-values that are included on our table. So now, how would we use this table? Well, first we need to locate our n value. Our n value has to be 8 or less. Given that we're restricted to a value of n being 8 or less, that means that our x values can only be 0 through n. So our x values are limited too, by the very nature of our n values being limited. So we locate n, we locate our value of x, or s, the number of successes. Once we have our values of n and x, we'll then just be looking at one row of numbers in that table. Within that row of numbers in the table, then we're going to take into account our p-value, and we'll find that across the top. The different p-values are in different columns. We'll line these up, and then we'll get our probability value. As a heads up, if you see 0 plus in this table, it really means the probability is very low. It's a very small number like 0.000064. So keep that in mind when you're using the table. You might get 0 plus, and you won't actually get to see the true value of that very small probability. Let's do an example here and use that table. This is the example in your textbook. I'm not sure who makes these examples, but this is another interesting one. So based on the findings of this analytics company, 60% of adults believe in the devil. In assuming that we randomly select 5 adults, we're going to use the table to do the following. A, we're going to find out the probability that exactly 3 of the 5 adults believe in the devil. Keep in mind this wording of exactly here in part A. In B, then, we're going to find the probability that the number of adults who believe in the devil is at least 2. So now we have exactly and then at least 2. Let's solve part A. In solving part A, in solving any of these problems, we need to determine the notation. Here we're selecting out of 5 adults. We're interested in 3 of those 5 adults. In the problem itself, we're told that 60% of adults believe in the devil. So for n, it's the fixed number of trials. Here n is equal to 5. For x or s, remember those are the same, this is a specific number of successes in those n number of trials. So x can be any whole number between 0 and n. Here we're interested in 3 of those 5 adults, so our x or s value is 3. For that lowercase p value, given 60%, we're going to take 60% divided by 100, we get 0.6. Remember, for lowercase p, we're interested in the probability of success in 1 of the n trials. Because 60% of adults do believe in the devil, then another way to think about this is if we have 100 people, 60 of those people do believe in the devil, 40 of those people do not. So really then that probability of selecting somebody at random, we have a 0.6 probability that they do believe in the devil. That means our lowercase p value here is 0.6. Remember that we need to be consistent, so x/s and p need to refer to the same concept of success. Here, our concept of success is that that person does believe in the devil. Then our x value is consistent with our p value. Because our x value is that exactly 3 of the 5 adults do believe in the devil. That's our measure of success here. Okay, so now that we have the notation, we know our n value, we know our x value, and we know our p value. Now, before we get this answer, we need to look at the table itself. So n is 5, so then we define n value here of 5. Our x value is 3, so we're at n equal to 5 and x is equal to 3. In the next step of figuring out probability, we need to locate our p-value. Our p-value is definitely not 0.01. Our p-value is actually 0.6. So when looking at the table, we would essentially ignore this column because that's not our p-value of interest. So then we find our proper p-value, but we also have to match it up with the x or s number of successes. So really then we're in n equal to 5, x equal to 3. In our column where our p-value is 0.6 up top here, then we go down and find our correct corresponding x value. The way that you'll see this is our corresponding x value is 3. Then our p of x value is 0.346. In the display in your notes, which hopefully you're looking at right now, it's a little bit more clear. So p values of 0.5, 0.6, 0.7, and it goes on through a p-value of 0.99. Given that this is our p-value, Then the next row down is x is equal to 0, x equal to 1, x equal to 2, and x equal to 3. So it actually is a pretty user-friendly way of figuring out the probability value. Going back to these steps here on this slide, so we first locate our n value, then our corresponding value of x. Once we have n and x, then we go to that corresponding p-value and we find the right probability value for our scenario, given a value of x and given our value of n. Okay, so using this table, n equal to 5, x equal to 3, p-value equal to 0.6, our probability of x is 0.346. That is our answer to part A. Let's continue on to part B now. So the probability of the number of adults who believe in the devil is at least 2. That really means we're interested in the probability of 2 adults believing in the devil, or 3 adults, or 4, or 5. We want to know the probability of all of these together. Here's essentially what I just mentioned. So the phrase at least 2 successes means that the number of successes is 2, or 3, or 4, or 5. Remember what we think when we hear or, that's our addition rule. So this scenario, or this scenario, or this scenario. This is as opposed to the multiplication rule. Remember for the multiplication rule, it's that this scenario happens, and this scenario happens, and this scenario happens, etc. So really, we want to know the probability of 2, or 3, or 4, or 5. When we say or, we're really going to add those probabilities together. Keep in mind our n value didn't change and our p value didn't change. Now though, we have 1, 2, 3, 4 different possible x values, and we'll still use this table to figure that out. So here's the equation we'd set up, the probability that at least 2 adults believe in the devil out of 5 that we selected. This is really the probability of 2, or 3, or 4, or 5. Using the addition rule, it's really the probability of 2 plus the probability of 3, etc. Then we can use this table. We already know our n value, we already know our p value. That means we're over here in our table. So then the probability of 2 is when x is equal to 2. That's 0.230. The probability of 3 adults believing the devil, that's an x value of 3, which we already looked at for part A, that's 0.346. The probability then of 4 adults believing in the devil is 0.259. The probability of 5 adults is 0.078. Because the wording was at least 2, then we have probability of 2, or 3, or 4, or 5. Rather than the probability of 2 adults believing, and 3 adults believing, and 4 adults, and 5. So because we use this table and we figured out all these probabilities based on our n value, based on our different x values, and based on our p value of 0.6, then we get our final answer here of 0.193. Okay, now I mentioned at the very beginning in the key concepts we cover is how to calculate the mean, standard deviation, and the variance for binomial distributions specifically. Fortunately, these equations are a little bit more straightforward than what you've seen before, where our mean, or mu, is n times p, our variance, or sigma squared, is n times p times q, our standard deviation, which is always the square root of our variance. In the same respect, the variance is always the square of the standard deviation. So our standard deviation, or sigma, is just the square root of how we calculated the variance. So for standard deviation, sigma is equal to the square root of n times p times q, where we first do this multiplication step and then take the square root. For the next example we'll go through, we're going to use this figure again. So to remind you of this, values are significantly low when they are the mean minus 2 times the standard deviation away. Values are significantly high when they're the mean plus 2 times standard deviations away. Then in the middle, the values that are not significant are between mu minus 2 sigma and mu plus 2 sigma. So in this lecture previously, we determined if the probability of 256 wins or more is significantly high. The key there is that we were dealing with probabilities. When we're using this idea of significance, this measure of significance, we only need to know the mean and the standard deviation. So let's do this example again, and we're going to find the mean and the standard deviation for the number of wins out of 460 games. We're also then going to use that range rule of thumb we just looked at on the last slide to find the values of separating the number of wins that are significantly low from those that are significantly high. Then we'll answer the same question again. Is the result of 252 overtime wins in 460 games significantly high? Okay, so for part A, we're going to find the mean and the standard deviation. We previously determined what's our n, x or s, p, and q values. If we hadn't just looked at this example, you would first need to figure out all of that notation. But we do have that notation here. So n is 460, p is 0.5, q is 0.5. Then all we need to know for our mean value is the number of trials n and our p value, where p value represents the probability of success in one of the trials. So our mean value here, 460 multiplied by 0.5, our mean value is 230.0 games. See that the unit was included here for the mean. So the unit is the number of games. Then for the standard deviation, we're going to use that formula. We need to know n and p and q now. Here's our n value, here's our p value, and here's our q value. We knew these were both 0.5 because we were told in the question that winning and losing is equally likely. In other words, the probability of success, the first possible category, is equal to the probability of failure, the second possible category. The standard deviation then is equal to the square root of all of these multiplied together, so that's equal to 10.7 games. Remember that we do include the unit here for standard deviation as well. What would the unit be for variance? Well, it'd be games squared. From what we just calculated, for random groups of 460 overtime games, the mean number of wins is 230.0 games. The standard deviation is 10.7 games. Let's go to part B now and use the range rule of thumb. Remember, when using the range rule of thumb here, the values separating the number of wins that are significantly low or significantly high are the values that are 2 standard deviations away from the mean. For values significantly low, they're less than or equal to the mean minus 2 times the standard deviation. For significantly high values, they're going to be greater than or equal to the mean plus 2 times standard deviation. It's important here to remember that this can be less than or equal to and greater than or equal to. So we just calculated our mean value, and we also just calculated our standard deviation value. So we have 230.0 games and 10.7 games, respectively. Then let's plug those values in. So we're going to take the mean minus 2 times sigma, and we get 208.6 games. That cutoff is for the games that are significantly low. It has to be equal to this or less to be considered significantly low. For significantly high, we take mu plus 2 times sigma, and we get 251.4. Remember our order of operations, we're always going to multiply these first and then do this addition or the subtraction. So what this number is telling us is that 251.4 games or more is a significantly high number of games. Now back to part C, which is a question we did answer previously using concepts of probabilities rather than the mean and the standard deviation. Here we're going to use the mean and the standard deviation and that range rule of thumb to determine significance. From what we just figured out in part B, we have how we classify a significantly low number of wins and how we classify a significantly high number of wins. So values in between this, 208.6 and 251.4, the values in between those are not considered significant. Now part C is asking about 252 games. Well, 252 is greater than or equal to 251.4. It's greater than, so we can say the result of 252 wins is significantly high because it's greater than or equal to the value of 251.4 games. Now, when we did this previously, we used probabilities instead of the mean and the standard deviation, and it makes sense that we got the same thing. We determined in both cases that 252 games is a significantly high number of successes. So now you should be comfortable both using a probability way of determining significance, both for a significantly high and low number of successes. The key is to figure out the probability and see if it's less than or equal to 0.05 or whatever other value we're given in the problem. It could be 0.01, it could be 0.09. Then just now we used the range rule of thumb to determine significance. For that range rule of thumb, we needed both the mean and the standard deviation value. Fortunately for these binomial probability distributions, finding the mean and the standard deviation value, those equations are relatively straightforward. All right, we are at the end of everything we're covering for exam 2, so everything in chapter 4, and then these 2 sections for chapter 5. Always email me or attend office hours if you have any questions at all. Once again, I highly recommend practicing with Excel. It's a truly useful tool for what we're doing in the semester, and you may even like using Excel for other cases too, so you could even do a personal budget. You can figure out weighted averages with Excel. Let me know how I can help, as always, and hopefully I will talk to some of you soon in office hours. Have an excellent rest of your day. I'll see you next time for chapter 6.